In this presentation, I am going to explain chopper control DC drive. How the chopper can be used to control the speed of DC motor. In chopper control DC motor, we are going to consider a separately excited DC motor. And chopper is a static device that converts fixed DC input voltage into a variable DC output voltage. And the choppers are used for the control of DC motors because of a number of advantages, such as it has got a high efficiency, flexibility in control, lightweight, and size is small, and it is have a quick response, and as well as it can be used for the regenerative concept, that regenerative drawn to a very low speed can be used. Now, chopper control DC motor drives have an application in servos, traction. The wide application is the for DC separately excited DC motor, separately excited motor controlled by choppers. Now coming to the circuit here, in a chopper circuit here, DC source, that is represented by VDC, and that's connected to a motor. The motor equivalent circuit is represented by RA, armature resistance, LA, armature inductance, and E is the back EMF. And across that one, a freewheeling diode is connected, and the voltage across the armature is represented by VA, and the current through the armature is represented by IA. And the chopping action, the chopper that is used by the switch, a transistor is using as a chopper switch. When the switch is on here, what happens is that the diode does not conduct, that's getting reverse bias, and the voltage V that will be coming across the armature, and that is why you are getting a voltage across the armature equal to V. Now at T equal to T on, the switch is off. As the switch is off here, what happens is that because of the energy stored in the inductance, that will be forward biasing this diode, freewheeling diode, and that will be circulating a current through this, through the motor and through the freewheeling diode. And in that case, previously the current was, when it is on, current was increasing from IA1 to IA2. When it is off, the current is decaying from IA2 to IA1. At that time T equal to, after one time period, it is coming back to the original value. Therefore, this is the voltage across the armature, and this is the current through the armature. Now, the duty ratio is defined as the on period divided by the total time period T. For T on by T is the duty ratio. Now, you can find out what is the average voltage that is coming across the armature, which is nothing but 1 by T integral 0 to T on V dt, or that is equal to delta times V, where delta is called the duty ratio, T on divided by total time period. Therefore, by changing the duty ratio delta, you can vary the average voltage coming across the armature. Now, this voltage is related to the speed of the motor, and a separately excited motor, omega m is given by VA divided by K minus RA divided by K square into T. VA is the armature voltage, K is a constant, RA is the armature resistance, again T is the torque. Therefore, it is equal to delta V divided by K minus RA divided by K square into T. As you change the delta duty ratio, this delta V that will be changing, thereby you can change the speed of the motor. That is the basic principle of chopper control. Here VA is the armature voltage, the constant K equal to KE into phi, where KE is given by P phi divided by 2 pi into A. A is the number of parallel paths and P is the number of poles, that is the total number of conductors. RA is the armature resistance, and torque is the torque. T is the torque in Newton meter. By controlling the duty ratio delta, you can control the speed of the motor, separately excited DC motor, by using this chopper. As I explained in the previous slide, during the on period, the switch armature voltage, period of the switch, the armature voltage VA is equal to V, that is the DC bus voltage, DC source voltage, that is equal to V, and armature current increases from IA1 to IA2. And here the corresponding equation governing the current is given by RAIA plus LA DIA by dt plus E equal to V, that is between 0 and T on. And when the switch is off here, when the transistor switch is off here, there will be a current through the freewheeling diode, and that current is governed by the equation RAIA plus LA DIA by dt plus E equal to 0, that is between T on to T. Therefore, these are the two equations that governs the current through the armature IA. This is during the on period and this is during the off period. Therefore, at t equal to t off, the switch is at t equal to t on, that is after that one, the switch is turned off and the motor current freewheels through the diode TF, and armature voltage is 0 during this interval, and the motor current is decreasing from IA2 to IA1. Therefore, chopper control separately excited DC motor, in that one, during the on period, the voltage V is applied across the armature, and during the off period, the voltage across equal to 0, and the average voltage can be controlled by changing the duty ratio, that is equal to delta V, and by changing the duty ratio delta V or delta here, V is a constant. As you change the duty ratio delta, you can vary the speed of the motor by the equation. It is equal to delta V divided by K minus Ra by K square into torque. This is the equation governing the torque versus omega m. And here you can see that one, it can be operated only in the first quadrant. That is, always you can make the voltage positive. You cannot make the voltage negative. You can, even the current will be always in this direction. The current is always flowing into the armature. Therefore, it can operate only in the first quadrant operation is possible. That is, for forward motoring is possible. In this case, as delta is increasing, this voltage, that delta V is increases, and thereby you can see that one, as delta increases, the omega for a given torque, as delta increases, the speed is increasing. So this depicts the relation between torque and the angular speed omega n for different duty ratio. That is speed torque characteristics of chopper separately excited DC motor during the motoring operation. What I explained previously, that is the motoring operation, there we used a chopper, we call it as class A chopper. But here this is called class B chopper, that is used for regenerative braking. That's called class B chopper, in which is usually that one, the positions of diode and transistors now reversed. Other thing is that the diode polarity is also reversed. The diode that is driving a current from the motor into the source. The current is made to flow from the motor into the source. That is, the diode direction is like that one, and this is the switch that is coming across the motor. Therefore, when here also, when the switch is on here, as the transistor switch is on here, you can say that one, the voltage across the armature is equal to 0 because it will be short circuited. Therefore, the voltage across the armature is equal to 0 when it is during the on period, and when it is, then what happens is that this will be driving a current because motor is running, and here there is an excitation is there. That is why it is working as a generator. During that period, that will be driving a current through this, in this direction. That will be current, that will be driving a current in this direction, that will be driving in this direction, and that will be storing an energy in the inductor. That is what is happening when it is transistor is on. When transistor is off here, whatever this energy stored in this one, that will be forward biasing this diode, and that will be driving a current in this direction, or the current flows from the motor into the source. That is what we call it as regenerative braking as such. Therefore, during the off period, the voltage across the armature is now, during the off period, this is connected to this one, or you are getting a voltage V is the VA is equal to V. Therefore, this is the voltage across the armature in the case of class B chopper. During on period, the voltage equal to 0. During off period, the voltage is equal to the DC input voltage V. Now, during on period, the armature voltage VA equal to 0, and armature current will be increasing from IA1 to IA2 during on period of the switch to IA2. And DC machine works as a generator, and a part of the energy is stored in the armature inductance, and the remainder is dissipated in the armature resistance. That is what is happening during the on period of this switch. And when the switch is turned off, the armature current flows through the diode D and the source V, and the armature current decreases from IA2 to IA1. That is, the current decreases from IA2 to IA1, and the stored energy in the inductance and the energy supplied by the machine is fed to the source. That is, energy is feeding back into the source. That is what we call it as regenerative braking. During that period, the voltage across the armature is same as the DC source voltage, capital V. Continuing class B chopper, here the duty ratio is defined as, delta is defined as this period, that is during which the voltage across the armature comes the V, or this period means T minus T on divided by T. That is the duty ratio during the, in class B chopper. And the armature, the average armature voltage, as you know that average armature voltage is given by 1 by T integral T on to T VDT, or if you substitute that one, that will be getting, it is equal to this delta times V. That is the average voltage that is coming across the armature. Now, yes, you know that one, what is the current through the armature? That is, always the current is in this direction. Current through the armature that you can get by actually this KVL, if you apply this voltage E plus delta V, E plus delta E, sorry, E, this voltage, no, that is this, whatever this voltage plus and minus here plus and minus, substituting that, this, applying the KVL to this loop, you will be getting the armature current IA is equal to E minus this delta V, that is the whatever this voltage comings, divided by RA, that is E minus delta V by RA, that will be current is in this direction. And IA has reversed, so the torque is also reversed, because the torque produced by the motor is now reversed, because armature current has been reversed. Therefore the torque produced is equal to minus K times IA, or the equation for the speed omega m equal to delta V divided by K minus RA by K square into T. Therefore that is the equation relating the omega m, angular speed, as well as the torque. And in that case you can see that one, that is working in class B chopper, this motor is working in the second quadrant, or it is called forward regenerative braking. This is the forward regenerative braking. As the duty ratio increases, we can see that one, that braking action of that one. In that case, the power is flowing from the motor into the DC source. For class B chopper is the regenerative braking chopper. Previously we have seen class A chopper and class B chopper. Now if you combine these two things, we'll be getting class C chopper, that's also called two quadrant chopper, class C chopper, that can be used for motoring as well as regenerative braking. In that one, here you can see that one, this here S1 and D1, that is S1 and D1 will be constituting the forward motoring, and S2 and D2 will be constituting the regenerative braking or class B type. Here there are two switches and there are two diodes that are connected across that one, and this is the motor equivalent circuit, RA, LA and back EMF E here. Therefore here as you see that one, when S1 is on, you will be getting a positive voltage here, or either when S1 is on, or if there is a diode D2 conducts here, you will be getting a positive voltage. Now if S2 is on, or if D1 conducts here, you will be getting zero voltage across the armature. Therefore armature voltage can be either V or it is equal to 0. Now let us see the current waveform here. The current waveform here, assume that this is the current waveform, that is certain duration current is negative, then certain duration current is positive. Even with a positive voltage, you can see that one certain duration current is negative, certain duration current is positive. Therefore here in this case, when current is negative and voltage is positive, means that D2 is conducting, that is during this period D2 conducts. Similarly from here to here, voltage is positive, similarly the current is also positive, then S1 will be conducting. Similarly during this period, voltage is 0 and current is positive. Voltage is 0 and current is positive means that current is positive. Current is positive means current is direction. In that case, the diode D1 will be conducting. The last case here, voltage is 0 and current is negative. Therefore here S2 will be conducting. Therefore depending upon the voltage as well as the current polarity, the switches either S1 or S2 or D1 or D2 conducts. Therefore A combination of the Class A and Class B chopper provides both motoring and regenerative braking operation in forward direction. Both are in forward direction. This is a two-quadrant chopper torque versus speed characteristics, and this region is called the motoring operation, and this region is the regenerative braking operation. As duty ratio changes, for a given torque you can change the speed. Therefore, this is the Class C type of chopper. Continuing Class C chopper or two-quadrant chopper here. For forward motoring operation, switch switch S1 is controlled. That is, switch S1 is controlled for forward motoring operation. For braking operation, this switch S2 is controlled. Therefore, these are the switches. For motoring operation, S1 is controlled. For braking operation, S2 is controlled. Now, shifting control from S1 to S2 shifts the operation from motoring into the braking and vice versa. And in servo motor applications, where the transition from the motoring to braking and vice versa is required, especially that is a servo motor application, the frequent change from motoring to braking as well as braking to motor is required. There you have to control the switches from S1 to S2 and S2 to S1. Let us see how does it. This is the voltage across the armature, and as I already explained, this is the current through the motor. Continuing two-quadrant chopper, Class C chopper for motoring and regenerative braking here. During a period T, switch S1 is on for a duration delta T and S2 is on for a delta 1 minus delta T duration. For S1 is on for delta T and 1 minus delta of times T is, this is on, where delta is the duty ratio of the switch S1. From 0 to delta T, motor is connected to the source and either through the switch S1 or diode D2 depending upon the polarity of the current. This is current, this is connected to the motor either through the switch S1 or through the D2. That depends upon the polarity of current. If polarity of current is positive, through S1, and if polarity of the current IA is negative, through D2. That, and during this operation, that's called the motoring operation of the motor current, that depending upon the polarity of the motor current, it will be either through S1 or through the D2. Since during this period, the voltage V is more than the back EMF E, during this period, the rate of change of current is positive. That is why the current is increasing from the rate of change of current is positive since V is more than capital E. From delta T to T, motor armature is shorted either through D2 or through S2, either through D2 or through S2, that is shorted. And during that period, the voltage, armature voltage will become 0. During that period, you can see that the back EMF will become more than the voltage V during this period, and the rate of change of current, that is the rate of change of current, will become negative. Therefore, the current is decaying like that one. That is what is happening when it is on and S1 is on as well as S2 is on. Continuing two-quadrant chopper here. The voltage, armature voltage VA is equal to delta times V, where delta is the duty ratio of the switch S1, and the armature current IA equal to delta V minus C divided by RA. And for motoring operation, IA is positive. As you know that one, IA is positive means that delta V should be more than E, or delta should be more than E by V. For braking operation, IA is negative, or delta V is less than capital E, or delta is less than E by V. Therefore, and the transition occurs from motoring to braking or braking to motoring. That occurs when delta equal to E by V. When duty ratio equal to E by V, that will be changing from motoring to braking, either motoring to braking or braking to motoring. Now we are going to explain four-quadrant chopper, that's also called Class C chopper. Now coming to the circuit diagram of four-quadrant chopper, there will be four switches S1, S2, S3, S4, and similarly four diodes are here. D1, D2, D3, D4, and the motor is connected between these points. And here we are assuming that armature resistance is negligibly small. That is why RA is eliminated for the back EMF and armature inductance. The voltage across VA, that is the voltage across the armature, is equal to VA, and current through the armature equal to IA, and V is the supply voltage. Now, 4-quadrant operation means that you can have a in torque versus omega plane is there. Similarly, the same thing that here voltage axis is there, current axis is there. Therefore, if you make the current positive as well as voltage positive, it will be working in a forward motoring region. So this is a forward motoring region. Voltage is positive and current is positive. And similarly, the torque is also positive and omega m is positive. Now, the second quadrant operation is that it is called forward regeneration. In that case, voltage is positive and current is negative, or and speed is positive and torque is negative. Now, coming to the third quadrant operation, that's called the reverse motoring. Here, both current and voltage both are negative. Current is negative as well as voltage is negative, meaning that speed is negative and torque is also negative. This is called reverse motoring. The fourth quadrant is called reverse regeneration. In that case, current is positive but voltage is negative, means that speed is negative and torque is positive. Therefore, these are the 4 quadrant of operations that can be implemented by using a circuit like this. This is called 4-quadrant chopper, or that's also class C type chopper. Now let us, in this chopper, both armature voltage and armature current may be either positive or negative. You can make positive voltage or negative voltage. Similarly, you can make positive current or negative current. Thereby, this motor can be operated in 4-quadrant regions. Now coming to that one, first one, quadrant 1, that is the first quadrant operation, forward motoring operation. What we are doing is that the switch S1 is controlled. That is, always just to remember that which quadrant we are operating, that particular switch is being controlled. That is why the switch S1 is being controlled and the switch S2 and S3 are kept off. S2 and S3, that switches are kept off, and here S1 is operated at a very high frequency and S4 is kept on. That is, you are making S4 is kept on and you are controlling the switch S1. And by doing this one, the corresponding equivalent circuit is like this one. A voltage source is there, S1 is there, this is you are controlling the switch, and here the switch S4 is permanently closed here, and the diode that is coming, the diode D4 is coming. This is the motor. And in the first quadrant operation, you are controlling the duty ratio of this switch. This S1 is you are controlling. Thereby, you are controlling the voltage across the armature and current through the armature. Both are in positive direction. That is why that will be working in a first quadrant operation. Coming to the second quadrant operation, that is, it's called the forward regeneration. In that case, you are getting a positive voltage VA and negative current IA. For getting that one, but we have to control the switch, which is S2 is to be controlled. That you are controlling the switch S2. S2 is controlled at very high frequency, and that is we are controlling the duty ratio of this S2, and all other switches, that is S1, S3 and S4, all are kept off. That is for the second quadrant operation, and S3 is control, on and off control is done, and we are controlling the duty ratio of this S2. You will be getting the average voltage, that is VA average voltage will be positive, but IA will be negative. The current will become negative. You will be getting negative current through the armature, because always the current is in this direction. You can see that one. So switch is like this one. The current is always in the direction. Therefore, here if the switch is controlling, if the current will be in this direction. If this is off, the current will be in this direction. Always the current through the motor will be always here you are getting the IA is negative. You are getting a negative current of IA and you are getting a positive voltage. That is the second quadrant of operation. Now coming to the third quadrant of operation, we have to do the E is to be reversed. That is back EMF is to be reversed. That is third quadrant operation means it is called the reverse motoring. The reverse motoring, that here E is reversed, and the switch that is to be controlled is, as you know, that it is always S3 is to be controlled. That is, you are controlling the switch S3, and here S1 and S4 are kept off and S2 is kept on. These are the switch positions, and here we are to control the S3. You are controlling the switch S3, or duty ratio of the S3 you are controlling. By controlling this one, you can get the average voltage is equal to, this average voltage VA is equal to negative. Similarly, average current is equal to negative. You are getting negative voltage as well as negative current. Always the current will be in this direction, and you will be getting a voltage, a reverse voltage. That is why it is made to work in the reverse motoring operation. That is, this is called a quadrant 3 operation. The last quadrant 4 operation means called, it is called the reverse regeneration. In the reverse regeneration, as you know, that voltage should be negative and current should be positive. Therefore, in order to get quadrant 4 operation, again here the polarity of E is to be reversed. You have to reverse the polarity of E, and here you have to control S4 is to be controlled, on off control. Therefore, you have to control the duty ratio of the S4, and all other switch S1, S2 and S3 all are kept off. Therefore, by controlling the duty ratio of this switch S4, you can control the average voltage across the armature and current through the armature, but voltage is always negative and current is positive. Therefore, it can made to work in a reverse regeneration mode. Therefore, these are the different quadrants in which the 4-quadrant chopper can work. Coming to the problem on 2-quadrant chopper fed separately excited motor. Now the problem is a 230 volt, 960 rpm, 200 amperes separately excited DC motor has an armature resistance of 0.02 ohms. The motor is fed from a chopper which provides both motoring and braking operations. The source has a voltage of 230 volt. Assume a continuous conduction. The first one, calculate the duty ratio of the chopper for motoring operation at rated torque and 350 rpm. Calculate the duty ratio of the chopper for braking operation at rated torque and 350 rpm. If maximum duty ratio of the chopper is limited to 0.95 and the maximum permissible motor current is twice the rated current, calculate the maximum permissible motor speed obtainable without field weakening and also the power fed into the source. This is the question. Coming to the solution, first you have to calculate what is the back EMF corresponding to the rated condition. I forgot to include that one. That you can calculate. That is, for the rated voltage and rated speed, E B equal to E plus IARA. The supply voltage, that is DC voltage 230 volt equal to E plus IA into RA, that is 200 into 0.02 ohms. From that equation, you can calculate what is the back EMF corresponding to the rated condition. And if you substitute in that equation, you will be getting the corresponding back EMF equal to 226 volt. That this is a 226 volt is the back EMF corresponding to the rated condition. That's to be included here. Now, coming to the first part of the question, calculate the duty ratio of the chopper for motoring operation at rated torque and 350 rpm. Now, corresponding to 350 rpm, you have to calculate what is the back EMF. That is equal to 226 divided by 960 into 350. It is equal to 82.4 volt. This is the back EMF corresponding to the speed 350 rpm. Okay. Next, here to calculate what is the motor terminal voltage. Motor terminal voltage VA is equal to nothing but the back EMF plus IARA. Back EMF you calculate, that's equal to 82.4 volt. Therefore, 82.4 volt and rated condition is called operation at a rated torque. That is why the current is rated what? 200 into 0.02 RA. Then you will be getting it is equal to 86.4 volt. This is the terminal voltage, required terminal voltage, and the input voltage, you know, that's equal to 230 volt. Then you can find out what is the duty ratio. Therefore, the duty ratio is given by 86.4 volt divided by 230. That's equal to 0.376. Second part of the question is the braking operation, and the speed is same as 350 rpm. Since the speed is 350 rpm, the braking operation is braking operation. It is the back EMF is same as the previous case, 80. Here back EMF is 82.4. But since the braking operation, can say that the current polarity now reverses. That is why the equations now becomes VA equal to E minus IARA. Therefore, the back EMF 82.4 is the minus IARA. 200 is the rated torque is given. Therefore, 200 into 0.02, or you will be getting it is you'll be getting it is equal to 78 watts. You'll be getting it is 78 watt. 78 volt is the, and 78 volt is the voltage, armature voltage corresponding to this braking operation, and corresponding duty ratio delta can be calculated by 78.4 divided by 230 equal to 0.34. The third part is that corresponding to the maximum duty ratio is given 0.95 in the problem. Therefore, the maximum available voltage is given by 0.95 into 230 equal to 218.5 volt. Now the corresponding back EMF you can calculate, which is equal to 218.5 plus the current, as you are telling, it is equal to twice the torque it is written. That is why it is equal to twice into 100 plus it is equal to IA, twice the 100 is the current, that into, that is IA equal to twice into 100, and here into RA. That is, you have to calculate that much current into RA. That is, this is not required, and that is, you will be getting the back EMF is equal to 226.5 volt. Therefore, the maximum permissible speed corresponding to this back EMF you'll be getting, can calculate, it's equal to 962 rpm. Therefore, this is the speed corresponding to maximum duty ratio, 962 rpm. Now, assuming the lossless chopper, the last part of that one, the power fed into the source, that is given by, it's equal to VA into IA, that is equal to 218.5 into 400, that is twice that current, load current is equal to twice 400, it is equal to 87.4 kilowatt.